Welcome to all. Today we are going to see Laplace transform. So many equations is transformed into the simple equation. So that one is to use widely the many application in the engineering field, like the Fourier transform, Z transform. So now we are going to see the Laplace transform. The French Newton, Pierre, Simon Laplace. So he invented the Laplace. Developed mathematics in astronomy, physics and statistics. Began work in calculus, which lead to the Laplace transform. Focused later on celestial mechanics. One of the first scientists to suggest the existence of black holes. So he is the found the Laplace transform. So his name Pierre Simon Laplace. So why use Laplace transform? So we transform into the some another equation. So find a solution to differential equation using algebra. Relationship to Fourier transform allows easy way to characterize systems. No need for convolution of input and differential equation solution. Useful with multiple process in system. So find the solution. Any differential equation is given to find the solution. Find the solution is nothing but to find the value of x using the basic algebra. And is a relationship to Fourier transform allows easy way to characterize some systems. And no need for convolution of input and differential equation the solution. And process in system in various. Now how to use Laplace? Find a differential equation that describe system. Which of the system is given? Find the differential equation. Obtain Laplace transform. Perform algebra to solve for output or variable of interest. Apply inverse transform to find solution. So function first is given means to find the Laplace transform, and after that again we get the similar function. If we take the inverse Laplace transform, we get the function of x or function of t. Okay. So what is the basic concept of Laplace transforms? So important analytic method for solving a linear ordinary differential equation. So we are familiar about the differential equation. So differential equation is nothing but it contains a differential operator. So here the ordinary differential equation. Ordinary differential equation is nothing but is a differential equation which involving a single independent variable. So that is called ordinary differential equation. And the linear, the order of the equation is the power value is 1. So that is called linear ordinary differential equation. And application to non-linear ODE. So non-linear, the power's value is different is given. So must linearize first. Laplace transforms play a key role in important process, control concept and some techniques. So some examples: transfer function, we change a function into the another function, and frequency response, then control system design and stability analysis. So what are Laplace transform? What is the basic formula? F of s equal to L of f of t is equal to integration of 0 to infinite f of t e power minus st dt. And second one is inverse Laplace transform. F of t equal to L inverse of f of s equal to 1 pi 2 pi I or j. We take the integration sigma minus j to sigma plus j f of s e power st ds. So here t is a real, is positive value, and s is complex. Inverse requires complex analysis to solve. Note that the transform f of t is mapping into f of s, capital F of s, where t is integrated and s is a variable. So conversely, f of s implies f of t. Here t is a variable and s is integrated. So here assumes f of t equal to 0 for all t greater than 0. So here, so this formula is important. F of s equal to L of f of t is equal to integration of 0 to infinite f of t e power minus st dt. So this is a basic formula for the Laplace transform. Second one is a formula for inverse Laplace transform. So that is f of t, L inverse of f of s equal to, we consider this same as in here, integration of 0 to infinite capital F of s e power st into ds. Okay. Next, so the previous slide is see the same definition here. The Laplace transform of a function f of t is defined as f of s equal to L of f of t is equal to integration of 0 to infinite f of t e power minus st dt, where f of s is a simple for the Laplace transform, L is the Laplace transform operator, and f of t is some function of time t. Here note that L is the operator. Operator is nothing but a transform a time domain function f of t into an s domain function, capital F of s. S is nothing but s is a complex variable, where s is nothing but a plus bj. We are familiar about the complex variable. A is a real part and b, what is a b? B is an imaginary part, and j is j. Some is notation is given I, here j. J value is nothing but j is equal to root of minus 1. That is our already familiar about the I square. I square value is minus 1. Same as in here. We take j equal to root of minus 1. Okay. So inverse Laplace transform, that is our familiar L inverse. So by the definition, the inverse Laplace transform, that is the operator L inverse, converts an s domain function back to the corresponding time domain function, that is our f of t. See the previous one. So this f of s, L of f of t, this is a Laplace transform. Inverse means this L is go to the left hand side. What we get? L inverse of f of s is nothing but f of t, and formula is 0 to infinite. Here the f of s, this function will come in here, f of s e power plus st dt. That is our inverse Laplace transform. Okay. So some common functions, Laplace transform of some common functions. First one, constant function. Let f of t equal to a is some constant. Then from the definition of the Laplace transform, in the previous definition, Laplace transform. So L of a. So first find L of a. So integration of 0 to infinite. What is our f of t? Is a. So a into e power minus st dt. Here a is constant value. We take outside of the integral. So a. And what is the integration of e power x? We get the e power x. So e power minus st divided by, what is the t coefficient? Minus s. So divided by minus s. And after that apply the limit 0 to infinite. So first we apply the upper limit value infinite replaced by t. What we get? E power minus infinite. E power minus infinite value is 0. So the first term will be 0. Then minus of, now to apply the lower limit value 0. So minus a by s. If we apply t value 0 in here, what we get? E power 0. E power 0 value is 1. So minus a by s. So here minus and minus plus a by s. So what is the formula for L of a? L of a is a by s. So if we take Laplace transform the some constant function, our answer is some constant by s. So here what is L of 1? L of 1 is nothing but 1 by s. L of 2, 2 by s. L of 3, 3 by s. If we replace any n by a value, we get the corresponding Laplace transform. So this function is constant function. Okay. Next one, step function. The unit step function is widely used in the analysis of process control problems. So it is defined as s of t equal to its value 0 for t is less than 0. If we take the time is less than 0, fractions of seconds we take is a value of 0. Suppose t value is greater than or equal to 0, its value is 1. So this is called step function. So because the step function is a specific, it's a special case of a constant, it follows from that. So L of s of t is equal to 1 by s. So s of t here we consider its value is 1 by s. Next, the derivatives. So this is a very important transform because derivatives appear in the ODE. Already familiar with the ODE, ordinary differential equations. We wish to solve in the text. It is shown that. So L of df by dt. Some function is given. L of df by dt. So we take the direct formula. S into f of s minus f of 0. So f of 0 is nothing but that is our initial condition at t equal to 0. So this is a first derivative. So first derivative formula L of df by dt equal to s into f of s minus f of 0. So similarly for higher order derivatives, suppose I take t power n. So L of t power n f by t power n equal to s power n f of s minus s power n minus 1 f of 0 minus s power n minus 2 f power 1 of 0, then minus and so on, minus s f power n minus 2 0, then minus f of f power n minus 1 0. So this is a common for nth order derivative. So it's a first order derivative. Second order derivative means what we get if we apply n value 2. So L of d square f by dt square. So s square f of s minus s f of 0 minus, here there is no term, s power 0 is 1. So f dash of 0. So that is the second order derivative. So here where n is an arbitrary positive integer and fk of 0 equal to is t power k f by dt power k and t equal to 0. So in here special case in here, all initial conditions are 0. We consider the final is the first starting, the condition is 0. Suppose f of 0, f power 1 of 0, f power 2 of 0 and so on, f power n minus 1 of 0. Then so L of t power n by f by t power n equal to s power n into f of s. So so these all the slides, these all the values will be 0. This value 0, second value 0, third and so on, all the values 0. Only we get L of t power n by f equal to f by dt power n equal to s power n into f of s. Okay. So here in process some control problems we usually assume 0 initial condition. For the reason this corresponds to the nominal steady state when deviation variables are used. Yes. Next one, exponential function. So previous one we saw the differential equation and the previous one step function. Now exponential function is nothing but e power x. So f of t, consider f of t equal to e power minus t minus p g where b is greater than 0. Then L of e power minus p g. This value is equal to integration of 0 to infinite. What is your f of x? E power minus pt, e power minus st dt. So these both one are the same base e. So to add the powers. So e power and take the common value minus t, e power minus what is the remaining b plus s of t dt. Okay. Now take the integration. What is the integration of e power x? Same e power x. So e power minus ps of t divided by what is the t coefficient? Minus bs minus b plus s. Okay. So that is a constant value we take and 1 by b plus s minus e power minus b plus s t. So limit value 0 to infinite. So first to apply the upper limit value infinite in here. If replace t value is infinite, what we get? E power minus infinite is 0. Then minus to apply the lower limit value 0 in here. Replace t value 0, e power 0. So that's e power 0 value 1. So already that we apply the upper limit, then minus of lower limit. So that minus and minus, what we get? Plus. So our answer is 1 by s plus p. So exponential. Yeah. So Laplace transform, that is the exponential function e power minus pt equal to 1 by s plus p. Suppose here we consider some p values are 2. So L of e power minus 2t. What is our answer? 1 by s plus 2. Suppose p value 3. So L of e power minus 3t equal to 1 by s plus 3. Fifth one, rectangular pulse function. So it is defined by function f of t is value 0 for t less than 0, h for 0 less than or equal to t less than tw. So value is 0 for t is greater than or equal to tw. The rectangular pulse function. Okay. So that is a rectangular shape. If we take some points here, we consider the x-axis and the y-axis is a point is x comma 0. Here the maximum value is 1. So this point we consider is a y coordinate. So x-axis is 0. So is a point 0 comma 1, and in this point is our x-axis. So y coordinate is 0, 1 comma 0. So we join these 2 points, what we get? A rectangular image. So it is called rectangular pulse function. Okay. So the Laplace transform of the rectangular pulse is given by f of s equal to h by s 1 minus e power minus t w of s. Next, impulse function or Dirac-Delta function. Impulse or Dirac-Delta function. So the impulse function is obtained by taking the limit of the rectangular pulse as its width tw goes to 0, but holding the area under the pulse constant at 1. So let's we take h equal to 1 by tw. So let's delta of t, that is equal to impulse function. So L of delta of t equal to 1. So if we take any impulse function here, delta of t, so that's Laplace transform of that impulse function is value is 1. Next, the solution of ODE by Laplace transform. So what are the procedure or what are the steps how to solve the ODE by using Laplace transform? So first one, take the Laplace L of both sides of the ODE. If anyone, the ordinary differential equation is given and some initial condition values are given. So take the Laplace simple L of both sides. Next, rearrange the resulting algebraic equation in the S domain to solve for the L of the output variable. So example, we take y of s. We take y of s or f of s or anything. So we apply that formula, Laplace formula, we get this one. Then perform a partial fraction expansion. If the equations values are given in the, then next we apply the partial fraction. So there is we familiar the 3 types of partial fraction. Type 1, factor is not repeated. So how to write in the partial fraction? A by plus b by. When the factor is repeated, we write a by plus b by plus c by. There is a repeated values which occur, and the third type is a by some x square plus a square. We never split x square plus a square. So is a third type. Third type, how to write that? Ax plus b by x square plus a square plus c by then the remaining factor. That are 3 types in the partial fraction. Next, in the final one, after we partial the values, then we apply L inverse on both sides. So use L inverse to find y of t from the expression for y of s. So these are the procedure for to solve the ordinary differential equation. Okay. So the previous one, that note on the some step functions in Laplace. So we need step function. Already we saw in the previous one. U of t value is 1, t greater than or equal to 0, and u of t equal to 0, t is less than 0. So used in conjunction with f of t implies f of t u of t. So because of Laplace integral limits. So this is a Laplace transform formula again. L of f of t equal to integration of 0 to infinite f of t e power minus st dt. Then some properties of Laplace transforms. Linearity property, first one, then scaling in time, then time shift, then frequency or S-plane shift, the multiplication by t power n, then integration, last one is differentiation. So properties of linearity. If two function is given, how to take the Laplace transform? L of c1 f1 of t plus c2 f2 of t, where c1 c2 are some constant values. f1 of t is the first function, f2 of t is the second function. We take Laplace transform. Okay. So first one we multiply L in here, so that is our L of c1 f1 of t and L of c2 f2 of t. So that's what is our linearity property. c1 L of f1 of t is nothing but f1 of s, c2 is constant, L of f2 of t is nothing but f2 of s. So proof is given here. L of c1 f1 of t plus c2 f2 of t. Here Laplace transform, familiar about the formula, L of f of t equal to, see the previous one, L of f of t equal to integration of 0 to infinite f of t e power minus st dt. So apply the formula in here. So here the c1 is constant, remain integration of 0 to infinite, c1 f of t f1 of t dt plus c2 is constant, integration of 0 to infinite f2 of t e power minus st dt. So c1, so this is the formula of Laplace transform, right? We write L of s or f1 of s. So this one plus c2 f2 of s. So that's our proof. So give the example, L of sin ht, hyperbolic function sin ht. So is the formula e power t minus e power minus t by 2, or nothing but 1 by 2 e power t minus 1 by 2 e power minus t. So take the Laplace transform, 1 by 2 is constant, L of e power t, and minus 1 by 2 is constant, L of e power minus t. So 1 by 2, what is the L of e power t? Already we saw the Laplace transform exponential formula. L of e power 1 or e power minus st is a formula 1 by s plus a. So here the positive value will come in, we take in the formula is a negative. Okay, e power 1 value 1 by s minus 1. Then here e power minus chi. So here 1 by s plus 1. We take opposite signs. Yeah. So this value is equal to 1 by 2. Here take the LCM. Here a plus b, a minus b. So a square minus b square. So multiply 1 into s plus 1, and here multiply 1 into s minus 1, and multiply minus means plus s minus s is cancelled. That is our 1 plus 1 2. So that 2 is cancelled. What we get the answer? 1 by s square minus 1. So Laplace transform of hyperbolic function sin ht equal to 1 by s square minus 1. Next, the properties scaling in time. L of f of at. So this is a formula 1 by e f of s by a. So proof, L of f of at equal to integration of 0 to infinite f of at e power minus st dt. So here we apply some substitution. So let u equal to at, and what is the t value? Cross multiply a, so u by a. Now differentiate on both sides. T differentiate dt. Here 1 by a is constant. U differentiate du. So this integration is changed into 1 by a, integration of 0 to infinite, and f of u e power minus s by u into du. Okay. So 1 by a. So this is our the Laplace formula. Is a value s means we take L of s. Here s by a. So that is our formula f of s by a. Yeah. So example, L of sin omega t. Yeah. So here omega t coefficient is omega, that is omega is constant, as compared to this example here a equal to omega. So 1 by omega, 1 by s by omega the whole square plus 1. That value is equal to 1 by omega. So here the square and take the LCM, s square by omega square. Take the reciprocal, we get omega square plus s square. So 1 by omega square by s square plus omega square. So 1 omega is cancelled. We get omega by s square plus omega square. Next, time shift. So L of f of t minus t naught and u of t minus t naught equal to e power minus s t naught f of s. So is a proof in here. L of f of t minus t naught u of t minus t naught equal to integration of 0 to infinite f of t minus t naught u into t minus t naught e power minus st dt. And integration of the limit values, here are both function. We consider f of t minus t naught and u t minus t naught. Compare of the function, what will be f of t minus t naught e power minus st dt. Let's here we take u equal to t minus t naught. So what is the t value? Minus t naught go to left hand side plus t naught. So u equal to u plus t naught. So integration of 0 to infinite and f of u e power minus s and u plus L theta into t naught into du. So e power minus s t naught is constant remaining 0 to infinite. Only function in terms of u in here. So f of u e power minus s u du. So e power minus s t naught. So this is the formula of Laplace transform. We write L of s or f of s. One example is given. L of e power minus a t minus 10 u of t minus 10. So is a direct value e power minus 10s divided by s plus a. Next properties s plane, that is a frequency shift. L of e power minus L of e power minus at f of t equal to f of s plus a. The previous one, if the value positive means here we get negative minus a. Is a minus a means this one is plus a. So proof L of e power minus at f of t equal to. So 0 to infinite e power minus at, what is the function is given? F of t e power minus f of, this is our function, e power minus at f of t, and in this formula e power minus st dt. So both here the same base e. So to add the powers, here minus at minus st, take the common value minus t. So e power minus of s plus at dt. So this is the formula of the Laplace transform. Here the value is s means f of s. Here the value s plus a, so f of s plus a. One example is given, L of e power minus at sin omega t equal to. Here we apply the formula. Yeah, we get the answer. Which formula we applying? The e power minus ax by a square plus b square a sin bx minus b cos bx. We take a value is a and b value is omega. After we apply the limit values, limit value is 0 to infinite. So we get the answer omega by s plus a the whole square plus omega square. Next, multiplication by t power n. So some is in derivative, differentiate. So L of t power n f of t equal to minus 1 power n d power n by ds power n f of s. So what is the proof? L of t power n f of t equal to integration of 0 to infinite t power n f of t e power minus st dt. So 0 to infinite f of t, here t power n e power minus st dt. So here next one, so minus 1 power n integration of 0 to infinite f of t, we take the integration of this one. So sorry, differentiation of this one, dou power n by dou s power n e power minus st. We take the differentiate of this function, we get again e power minus st. Okay, so e power minus st dt, then minus 1 power n dou power n by dou s power n integration of 0 to infinite f of t e power minus st dt equal to minus 1 power n. So this dou power n by dou s power n. So this is a formula of Laplace transform, that is our L of s or f of s. So one example based by the multiplication by t power n. So L of t power n u of t equal to, so minus 1 power n d power n by ds power n into 1 by s. So we apply this formula, or we get answer n factorial by s power n plus 1. So is the direct formula. Next, evaluating f of s, this is our L of f of t. So hard way to the integral. F of t value 1, what is f of s? So 0 to infinite e power minus st dt, that is minus 1 by s, that is our integration. E power x is e power x t coefficient is minus s, minus 1 by s. Now apply the upper limit value infinite, e power infinite is 0, then apply the lower limit value 0, e power 0 is 1, so that minus and minus plus 1 by s. Suppose f of t is 2 means f of s 2 by s, 3 means 3 by s, and f of t e power minus at, so what is the f of s formula? 1 by s plus a. And next one, f of t sin t, and f of equal to 0 to infinite e power minus st sin t dt. So that is our proof in here. So e power minus st du, then take the differentiation. So minus s e power minus st dt, and dv, then sin of 1 dt. And what is the v value? Again integration of this value, sin integration is minus cos. So 0 to infinite e power minus t sin t dt equal to, here we apply the integral by parts here, the formula in here, that is our remember. So integration of u dv equal to uv minus integration of v du. So what is the u value? E power minus st. And what is the v value? Minus cos t, integration of 0 to infinite, then the formula minus, then v du. What is the v value? Minus cos t, and what is the du value? Minus s e power minus st dt. So that is value here. So here apply the upper limit value infinite, e power minus infinite is 0, so neglect. To apply the lower limit value 0, e power 0 is 1, so e power minus st into 1, then minus s, here the same function here. Again we take the integration of this function. We take u equal to e power minus st, but we take the du, and this minus s e power minus st dt, and to find the dv, integration of this function. Yeah. So dv is this value, cos t dt, and we take the integration v is equal to integration of cos sin t. Here u value e power minus st, take the differentiate, minus s e power minus st dt. So therefore 0 to infinite e power minus st cos t dt equal to, what we get the final answer. Here also to apply the same formula, Bernoulli's, that here we apply integration by parts or Bernoulli's formula. Bernoulli's formula is for the value, the constant is n of means we use the Bernoulli's formula. So uv integration of 0 to infinite and plus s integration of v du. Yeah. So what we get the answer? E power minus st of 0, that term will be 0, then plus s, here apply the upper limit value infinite. So e power minus infinite is 0, again that is 1 minus s square, 0 to infinite e power minus st sin t dt. So here 1 plus s square, 0 to infinite e power minus st sin t dt equal to 1, and toss multiply we get 1 by 1 plus s square. And table of selected Laplace transform. So these are the the familiar, the values, f of t 1 by s, and f of t e power minus at u of t, that f of s is 1 by s plus a, and cos t u of t, so s by s square plus 1, and sin t u of t 1 by s square plus 1, cos x. So Laplace transform of cos t, s by s square plus 1, Laplace transform of sin t 1 by s square plus 1. This is a power n, already we saw that, to t power n. So L of t power n is nothing but n factorial by s power n plus 1. If n value is 0, what do you get? That is 0 factorial is 1 by s power 0 plus 1, 1 by s. If n value 1, 1 factorial by s power 1 plus 1, that is our s square. If n value 5, f of s equal to 5 factorial by s power 5 plus 1, 6, 5 factorial value 120 divided by s power 6. So f of t, that value is equal to delta of t, if and only if that implies f of s equal to 1. And these are the table, so the familiar values of the Laplace transform of the function. So L of 1 is nothing but 1 by s, and L of e power at 1 by s minus a, and L of t power n factorial by s power n plus 1, and L of t power p, there is a gamma is nothing but factorial. So gamma of p plus 1 by s power p plus 1, where s is greater than 0. Sin at is a formula, a by s square plus a square, cos at s by s square plus a square, and all the values s is greater than 0, and sin h at hyperbolic function, a by s square minus a square, s is greater than modulus a, and cos h a t s by a square minus a square, s is greater than modulus a, and e power a t sin b t b by s minus a the whole square plus b square, s is greater than a, and e power a t cos b t s minus a by s minus a the whole square plus b square, s is greater than a, and t power n e power a t, if n is a positive integer, would be n factorial by some s power. Here s value is replaced by s minus a power n plus 1, s is greater than a, and u of t is nothing but e power minus cs by s, s is greater than 0, and uc of t and f of t minus c e power minus cs f of s, and e power ct f of t f of s minus c, and f of ct 1 by c f of s by c. Already we saw that the property here nothing but f of at, here is f of ct is given, so a is replaced by c, right? So 0 to t f of t minus tau, some g of tau t tau, f of s g of s, so it's nothing but composite function of the two function f and g, and delta of t minus c is e power minus cs, and f power n of t s power n f of s minus s power n minus 1 f of 0 minus and so on minus f of f power n minus 1 0 minus t power n f of t, here f power n of s. So these are the familiar formulas of the Laplace transform. Next, you do an example, solve the ODE, ordinary differential equation. So the problem is given 5 dy by dt plus 4y equal to 2, and some initial condition is given y of 0 equal to 1. So first to take L of both sides, taking Laplace transform on both sides, but we get 5 into L of t, and here after replace 4 L of y equal to L of 2. What is L of 2 value? L of a is a by s, so L of 2 by s here. Okay. So L of dy by dt, that is a derivative formula, s into y of s minus y of 0. Y of 0 is nothing but 1. So 5 s into y of s minus y of 0 value 1 plus 4 into y of s equal to 2 by s. Next, to find the y of s, so multiply in here and multiply minus 5, that minus 5 go to right hand side is plus 5, and now consider the first and this time take the common value y of s. So what is the remaining? 5s plus 2 divided by s into 5s plus 4. Next, take L inverse. Take the L inverse on both sides. So L inverse of y of s is nothing but y of t. So L inverse of 5s plus 2 divided by s into 5s plus 4. So we saw the table values, y of t equal to, we applied here, the value is 0.5 plus 0.5 e power minus 0.8 t. Next, partial fraction expansion. The previous one we directly take the Laplace transform, here partial fraction. Yeah. So we familiar about the partial fraction in the school, the three types already. So here the problem is given in the first type, the factor is not repeated, the two factors are different factors. Right? So example, y of s, s plus 5 by s plus 1 s plus 4. So perform a partial fraction expansion PFA, s plus 5 by s plus 1 s plus 4. So some we take capital A or small a, or here we take alpha 1 by s plus 1 plus alpha 2 by s plus 4, where the coefficient alpha 1 and alpha 2 have to be determined. How to find alpha 1 and alpha 2? Take the LCM, and after that cross multiply, we assume and s plus 1 equal to 0, we get s equal to minus 1, and replace s equal to minus 1 here. So this time alpha 2 is neglected, we get the value of alpha 1. Then after that we take s equal to minus 4 and replace in here, then alpha 1 is neglected, we get the value of alpha 2. Okay, so that is that. So to find alpha 1, multiply both sides by s plus 1 and let s equal to minus 1. So alpha 1 equal to s plus 5 by s plus 1, s is replaced by minus 1, s replaced by minus 1 would get minus 1 plus 5 4, and here s value minus 1 plus 4 we get 3. So alpha 1 value is 4 by 3. So So to find alpha 2, multiply both sides by s plus 4 and let s equal to minus 4. So therefore alpha 2 equal to s plus 5 divided by s plus 1, and s is replaced by minus 4. Here s replaced minus 4 plus 5 you get 1, and minus 4 plus 1 you get minus 3. So our alpha 2 value minus 1 by 3. So after we found out the alpha 1 alpha 2 value, substitute in these equations, then we take L inverse on both sides, so we get the answer. If you take L inverse, what we get? Alpha 1. What is alpha 1 value? 4 by 3. So 4 by 3 is constant. L inverse of 1 by s plus 1. What is L inverse of 1 by s plus 1? That is our inverse Laplace transform. Okay. So L of e power minus t. And here alpha 2 value is minus 1 by 3. L inverse of 1 by s plus 4. What we get? E power minus 4t. So general, that is partial fraction. So consider the general expression y of s, numerator divided by denominator, n of s by d of s. So n of s divided by pi I equal to 1 to n s plus bi. And here some d of s is an nth order polynomial with the roots, denominator. So all being the real numbers which are distinct, so there are no repeated roots. Then the partial fraction equation is y of s equal to the same function sigma of I equal to 1 to n alpha I divided by s plus bi. So d of s is called the characteristic polynomial. So some special situations, two other types of situation commonly occur when d of s. In the denominator, complex roots will come. Complex root is nothing but bi, 3 plus or minus 4j, j value is equal to root of minus 1, and some repeated roots value given. So p1 equal to b2 some minus 3. For this situation, partial fraction equation has different form. We cannot use this format. Okay. Next example 2. So here the ODE differential equation, y triple dot is nothing but d cube y by dx cube plus 6 d square y by dx square plus 11 dy by dx plus 6y equal to 1 with the 0 initial condition resulted in the expression. Yeah. So what we get? Y of s equal to, we take taking Laplace transform on both sides. After that we have the expansion, we get y of s 1 by s into s cube plus 6x square plus 11s plus 6. The denominator can be factored. See the denominator. So s cube plus 6 s square plus 11s plus 6. So here we apply the synthetic division, or we take the common value here. We get the answer is easy. So s into s plus 1, s plus 2, s plus 3. Okay. If we apply minus 1 means that equation is satisfied. If we apply minus 2 is this equation is satisfied. If we apply minus 3 is this equation is satisfied. So the roots of this equation is minus 1, minus 2, minus 3. So write the factor s plus 1, s plus 2, s plus 3. So normally numerical techniques are required in order to calculate the roots. So y of s 1 by s into s plus 1, s plus 2, s plus 3. So this is also the type 1. The factor is not repeated, all the different factors. So alpha 1 by s plus alpha 2 by s plus 1 plus alpha 3 by s plus 2 and alpha 4 by s plus 3. Next to find alpha 1, alpha 2, alpha 3, alpha 4 value. After we find the alpha 1, alpha 2, alpha 3 value, we substitute here and take the inverse Laplace transform, we get the solution. So here alpha 1 value, after the simplification we get 1 by 6, alpha 2 minus 1 by 2, alpha 3 1 by 2, alpha 4 minus 1 by 6. So substitute these values in the previous equation. So alpha 1 value 1 by 6, alpha 2 is minus 1 by 2, alpha 3 is 1 by 2, alpha 4 is minus 1 by 6. So taking L inverse on both sides, so L inverse of y of s equal to L inverse of 1 by 6 by s minus L inverse of 1 by 2 by s plus 1 plus L inverse of 1 by 2 by s plus 2, then minus L inverse of 1 by 6 by s plus 3. So from the table we familiar about the value. L inverse of y of s is nothing but y of t. 1 by 6 is constant. What is the L inverse of 1 by s? Is nothing but its value is 1. So 1 by 6 into 1, 1 by 6. Then minus 1 by t is constant. L inverse of 1 by s plus 1. 1 by s plus 1 is e power minus at. So here a value is 1. So e power minus t. And here also 1 by 2 is constant. So So e power minus st, so sorry, e power minus 80, what is the a value is 2, so e power minus 2t, and here 1 by 6 is constant, so minus 1 by 6, LUs of 1 by s plus a, so e power minus 80, a value is 3, so e power minus 3t. So this is the solution. Some important properties of Laplace transform. The final value theorem. It can be used to find steady state value of a closed loop system. The providing that a steady state value exists. Statement of the final value theorem. So limit t tends to infinite, y of t. We apply up to infinite. Limit s of s tends to 0, s of y of s. So function we apply, t is replaced by infinite. Then we get limit s of y of s tends to 0, providing that the limit exists is finite for all the residue 6 greater than or equal to 0, where residues denotes the real part of complex variable s. So another one is initial value theorem. Final value theorem is nothing but here we take infinite, we apply t value infinite here, that function is tends to 0. Then initial value theorem, we apply t tends to 0, the function is going up to infinite. So some example for the final value theorem. Y of s function, the y of s is given, then y of infinite. Yeah. Here limit t tends to infinite, y of t. So limit we apply t tends to infinite is changed into s tends to 0, 5s by 2 by 5s plus 4. So we apply the 0 value after we take the common value of s, so that s is cancelled. So here that is 2 by s and 2 by 4, what we get is 1 by 2, 1 by 2 value is 0.5. Next, time delay. So time delays occur due to fluid flow, time required to do an analysis. Example, gas chromatograph. The delayed signal can be represented as y of t minus theta. Is value theta is nothing but time delay. L of y of t minus theta equal to e power minus theta is y of s. So some real applications. Previous one how to solve the ordinary differential equation, and then final value theorem, then time delay. Now the real life applications. In which field we apply the Laplace transform? First one is semiconductor mobility. The second one, call completion in wireless networks. So that's a time, simple of time. Yes. This step function and the scaling time, the time shift, both are used in the wireless network. That is our call completion in wireless network. And vehicle vibration on compressed rails, and behavior of magnetic and electric fields above the atmosphere. So example, semiconductor mobility. So motivation, semiconductor are commonly made with superlattices having layer of differing compositions. Need to determine properties of carrier in each layer. Concentrations of electrons and holes. Mobility of electrons and holes. Here is a diagram, you see the semiconductor mobility. The conductivity tensor can be related to Laplace transform to electron and hole densities. So the path which way the electron is going. Next, so some notations. The notations are is nothing but is a ratio induced electric field to the product of the current density and applied magnetic field. That is a rho is electrical resistance, H magnetic field, J is a current density, E applied electrical field, N concentration of electrons u mobility. So is a formula in here, u of x equal to rho of jx minus rh j of y, and e of y equal to rh jx plus rho of jy. Some equation manipulation. So is a rho is a formula 1 by n u n e mu, and r resistance is nothing but minus 1 by n e, and sigma of xx n e mu by 1 plus mu h the whole square, and sigma of xy minus n e mu square h by 1 plus mu h the whole square. So which one implies? We get j of x, that is the previous formula, jx. Sigma xx e of x plus sigma xy e of y, and jy minus sigma xy e of x plus sigma xx e of y. Next, assuming a continuous mobility distribution, and that s of, that is a plus mu, is a k plus e mu p, that is a mu plus, and suppose s negative means s minus of mu equal to k minus e mu n mu. It follows that. So is a sigma xx and sigma yy, we change, transform into sigma xx h, and integration from 0 to infinite from positive function negative function divided by 1 plus mu h the whole square d mu, and sigma xy of h equal to 0 to infinite s plus mu minus s minus of mu and mu h by 1 plus mu h the whole square into d mu. So these are the some applications in mobility. Okay, thank you.